are CFCs. Chlorofluorocarbons are man-made chemicals that were once used everywhere. For example, in refrigerator, air conditioner, and aerosol spray cans. They were originally loved by industry because they are non-toxic and don't catch fire easily. While they are safe to use in our home, they are very stable and don't break down easily too. And because of this, they eventually drift up into the upper atmosphere, where the Earth's protective ozone layer is located. How do they destroy the ozone layer? Once CFC reach the upper atmosphere, they emit high-energy UV light from the sun. This breaks the chemical bonds of the CFC, which called as photolysis. When CFC molecule break, it releases a chlorine atom, and this chlorine atom is like a recycling destroyer. And it can destroy up to 100,000 ozone molecules before it finally drifts away. The simple reaction has been shown in the slide. As you can see, the Cl is produced back and go to start destruction all over again. Why do we need to track them every year? First, because measuring the air is the only way to prove if that country is actually following the rules of Montreal Protocol or not. Second, we can predict the time's recovery. Currently, scientists suggest it will around the year of 2060 or 2070. Third, this acts as an alarm where we can find the cheaters who is causing the increase of CFC11 illegally for further investigation. What we want from this study? We want to find the source by using wine pattern and air sample to find exactly where the CFC gases are coming from. Next, we want to determine the gas is newly made or if it's just leaking out from all insulation plates that made decades ago. Lastly, we want to check the effectiveness of how quickly emission drop after interventions are made. What we want from this study? We want to find the source.
So for our data sources, we use three types of data. First, the primary source is the NOAA Global Monitoring Laboratory, which provides long-term atmospheric CFC measurements from 1979 to 2024 through a global network of monitoring stations located in remote areas. And then to verify our data, we use measurements from JMA Ryori Station in Japan as an independent validation source. Next, we also refer to the ORCID as a supplementary source to provide additional atmospheric halocarbon data and context. So for our study area, we focus on the global atmosphere. The data were collected from monitoring stations located across the northern and southern hemisphere, including Alaska, Hawaii, Ireland, Tasmania, Samoa, and the South Pole, with the JMA Ryori Station used for validation. Our study covers 45 years from 1979 to 2024, allowing us to observe changes in atmospheric CFC concentrations before and after the Montreal. So for the methodology part, which is the data processing, first we download the CFC datasets from NOAA and JMA. Then the data were cleaned to remove missing or invalid values, and then the annual mean concentrations were calculated from the monthly measurements. Lastly, we also perform cross-dataset validation to ensure the reliability of the results. And for the analysis, we use time series analysis to observe long-term trends, linear regression to determine rate of increase and decline. And lastly, anomaly analysis to identify unusual year-to-year variation.
The graphs show long-term trends of CFC11 and CFC12 from 1979 to 2024. CFC11 peaks around 1990 to 1994 at around 270 parts per trillion, then declines steadily. CFC12 peaked later around 2003-2005 at about 540 parts per trillion because it stays in the air longer. Between 2002 and 2012, CFC11 fell by approximately 2 parts per trillion each year, showing a sign of Montreal Protocol success. From 2012 to 2018, CFC11 seemed to decline at an unexpectedly slower rate than expected. Investigations traced a major portion of these unexpected emissions to unreported production in eastern China. By 2018-2020, after international pressure, the decline rate returned to approximately 1.7 parts per trillion per year. China's CFC12 emissions fell by 70% between 2016 and 2034. The trend is a direct result of global adherence to the Montreal Protocol.
Why do CFC 11 and 12 behave differently? Because they have different atmospheric lifetime. CFC-11 stays in the atmosphere for about 50 years, while CFC-12 remains for about 100 years. So, CFC-11 responds faster to emission reductions, while CFC-12 takes much longer to decline. Overall, the result shows that the Montreal Protocol has been successful in reducing CFC emissions. However, the slowdown in CFC-11 decline between 2013 and 2018 was caused by unreported emissions. Although progress has been made, some CFC-12 emissions are still unidentified. Therefore, continuous monitoring is important to ensure the recovery of the ozone layer.
The Montreal Protocol has been highly successful, resulting in a decline in global CFC-11 and CFC-12 concentrations. CFC-11 peaked in the early 1990s, whereas CFC-12 peaked around 2003-2005. The temporary slowdown in CFC-11 decline between 2012 to 2018 was caused by unreported emissions, mostly from Eastern China. After international action, the decline accelerated again, proving that monitoring and policy works. Recent data show China's CFC-12 emissions fell by 72% between 2016 to 2024. Year-to-year atmospheric measurements are the true test of environmental treaties. Without them, violations would go unnoticed.